Good morning, all. Yes, good morning, because this is a recorded lecture and I'm recording this in the morning session. Due to some personal reason, I might not be able to conduct today's, that is 14th October 2020 lecture at timing 4 to 5. So, hence, I'm recording this lecture and providing you with the recording so that the same time, that is 4 to 5, you can watch this recording, understand the concepts that are discussed, and maybe we can have a discussion over the contents in the Friday lecture. So let us begin. So in this session, I'm going to teach you how we can create recursive subroutines or recursive functions in Haskell. Okay, we have already seen one recursive function, but these are more than one that we are going to learn in order to understand how we can realize the recursion that we already know in C programming language, how we can realize the similar type of constructs in the syntax of Haskell programming language. As we earlier discussed, recursion is one of the key concepts in order to realize composite functions in functional programming, and hence we need to understand recursion in pretty details, and we should be able to write code using recursive subroutines. The other important fact that since in functional programming language, which are purely functional programming language, we do not have concept of iteration or repetition. So repetitive constructs are not there, like for loop, while loop, do while loop. Hence, we need to replace the iterations in terms of recursion. So that's the need of recursion in functional programming language, which are purely functional programming language, and they do not hold syntax for repetition control flow constructs. Okay, so let us begin. We already have looked at a code, which is, I'll just show you. Yeah, this one, which is factorial.sh. So here we see 4 implementation of factorials. This is factorial, factorial dash, factorial double dash, and factorial triple dash. So all these 4 implementations of factorial we will first look at, and then we'll understand how they differ from other declaration of factorials that we see. Okay, now let us begin factorial 1. So we have here factorial first definition of factorial n is equal to if n less than 2, then 1, else n into factorial n minus 1. Now if you look at this particular definition of factorial, this is just a single line, but this very well coincides with the way we will implement factorial in the recursive version using the if-else construct in C programming language. Only the thing is, since we are using if-else in Haskell, we are following the syntax of if-else in Haskell. So if-else in Haskell requires you to use 3 keywords: if, then, and else. Now, why I require this then is because in Haskell, we do not have block construct. We do not have brackets to enclose the condition. Hence, to separate out the if part from the else part, that is the true part from the false part, and the true part from the condition, we use this particular keyword then. So between if and then, these 2 keywords, I provide the condition, which can be any condition that you can evaluate as a Boolean condition, true or false. Then after then keyword and else keyword, between these 2 things, I provide all the statements that I want to execute or that I want to say the function returns when the condition is true. Those things I specify here. Then after else, rest of the things are the things that I need to execute whenever the condition is false, that I will be writing. Now if you see this function factorial n, if I want to check how it executes, I'll just copy this down and put it into a notepad so that I will let you be aware of how recursion executes. I know everybody is aware of recursion and we had seen this, so you might know what happens when we do make a application of this function. So factorial say we call this with 4 as input. Okay, so whenever I call factorial 4, my value of internally what happens, n becomes 4. Now as n is 4, okay, this n, I'll write rather n gets 4. Okay, so in equal to side, that is the right hand side, I will have this thing wherein n now will read as 4. So my condition that I'm going to evaluate is 4 less than 2. And when I evaluate this condition, this evaluates to be a false condition. As it evaluates as a false condition, need to say that it evaluates to be false condition, I need to execute or I need to return this, okay, to factor as a result of factorial 4. So now to compute result of factorial 4, when I instantiate it as factorial 4, my code will become n into factorial n minus 1, that it will become 3. So I need to write here 4. It will be 4 here, it will be 4 here. So since the condition 4 is less than n is less than 4 is less than 2 is false, factorial 4 will be returned as n into factorial 3, where n is 4. So 4 into factorial 3. Similarly, I will evaluate factorial 3, which will be nothing but, you can realize that it will be nothing but 3 into factorial 2, okay, which will later be 2 into factorial 1. Now, whenever I want to evaluate factorial 1, this is a particular evaluation, so I'm just commenting this. Here my n value is 1. So the equal to side becomes if 1 less than 2, then 1, else I have n1 into factorial 0, right? So this is how it will be substituted. So I'll be substituting for n value 1, and because of which this expression, which is if else expression, will read if 1 less than 2, then 1, else 1 into factorial 0. So this is how it will read. And since the condition 1 less than 2 is true, because 1 is less than 2, what will happen is this thing will be associated or returned to as factorial of 1. So I will be returning, or I will be saying factorial of 1 is evaluated as 1, and there is nothing more to evaluate after this. So I will say factorial 1 is 1, and I will put this value in line number 5. So put value of factorial 1 in line 5 above. So what we have is factorial 4 is equal to 4 into 3 into, pardon me, my laptop doesn't print 3 in the first hit. 4 into 3 into 2 into 1, and that is how we can write a recursive procedure for calculating a factorial. Here we have taken help of if else then construct that is available for us in Haskell. So we have control flow construct if else then, but we do not have the construct called as repetition, and that's why we are writing recursive definition of factorial. Okay, now if you see the second definition here, I hope this is pretty realizable. This second definition of factorial takes help of a library function in Prelude, which is called as product. So if you see here, now the second code, so this is the first code, first implementation, Okay. Now I have a second implementation. I'll just, sorry for that hissing sound in between. So now this is the second implementation. Okay. The only difference between first and second implementation, apart from the way it is defined, the factorial dash function is factorial dash function. We use an explicit, because we are expressing it as a programmer, explicit signature of the function. Whereas here, when we defined factorial, we did not specify the signature of the function. But what would be the signature of the function? So it will be factorial. Okay, as a type, the input is going to be always a number or an integer. So a type, which will be converted to another a type. So it is a mapping from a to a. And if I want to put any constraint, the constraint would be a must be a numeric type. Or I may say, if I don't want to write a generic representation, I may say it to be a mapping from an int to int. And if I write int to int, then I need not use this part. Okay, why I'm not writing num is because even float and double are num, and I can't apply factorial to those particular type of data, and that's why I will restrict it to int to int. Okay, fine. Now this is here. If we see the definition, instead of int we are using integer, because I want to have a factorial of any large integer. And mind well, this is not directly a recursive subroutine. It takes help of a prelude library function called as product, which just takes a list and reduces list to a number by multiplying each and every element with other. So I have a list of 1 up to n. So it's a range list, 1 to n. N is my input. So if input is say 4, the list will be 1, 2, 3, 4. And the product will operate on this list to reduce this list to 1 into 2 into 3 into 4. And that is how I'll compute factorial of n. Okay, so this is the second implementation. The third implementation, I'll also write it here itself, because the difference in second and third implementation is only of that of the signature. The signature for third implementation is, instead of integer, we are using int. So you'll say that, sir, ये तो हम आपने थोड़ा हमको Friday में बताया था. I'm repeating this because this is very important. We need to realize that one thing in Haskell can be written in many ways. And the other important fact here we need to realize is the library function that we are using, they must be internally somehow using the concept of recursion. Without that, even they won't be able to execute these particular code. So product internally also does the similar thing. Somehow its code, although it is not written by us, will be written by some standard programmer or a developer. He must have also used a recursive subroutine. Now what he does is he reduces or collapses this list to a number using multiplication. So later on we'll see that can we also write a similar subroutine what product does. Okay, so we'll see to it afterwards. Right now we will check the last kind of implementation. Okay, so this is another implementation of factorial. So factorial 0 is equal to 1 and factorial n is equal to, if n is less than equal to 0, then 1, else n into factorial n minus 1. Okay, this is kind of an overkill, but if I want to use the pattern matching concept of I guess there is one more factorial implementation. I'll just see. Yeah, there's one more factorial implementation. Yes. No, this is product. And I guess there is one more fact.hs. Okay, see. So this is another implementation. Fact 0 is 1 and fact n minus 1. So I'll just copy it down. Name of the function doesn't matter. Second, third